Hello, I'm Dhanya. So I'll be covering first two units, that is ultrasonics and acoustics and fiber optics. So first we'll start with acoustics. With respect to sound sensitivity, I'll try to just cover what's really important instead of going through everything because I think there's a lot that's there. Uh, so yeah, starting with acoustics in itself, what is it? Okay. So acoustic, it means to hear. So it relates to the science of sound. So when it comes to sound, you talk about the three terms, that is generation, propagation, and reception. So generation is just generating the sound. Propagation is transmitting the sound, how you transmit the sound through any medium, through what medium you transmit. And then reception is how a human ear receives the transmitted sound. Okay. So uh, I will just mention whenever I'm like going over these slides, if I think that that's important, I will read it for you for the exam or such. I'll just mention that. Okay, so as of now, just know the basic layout of what this chapter actually means. Okay, so in gaseous and liquid media, they propagate as longitudinal waves. As in, the waves are parallel to the initial wave pattern. Okay. And then the traverse wave, na, there is like a crest and trough, okay, which is perpendicular to each other. Okay. So in solid medium, they propagate both as transverse and longitudinal wave. Okay. So a sound wave is a kind of energy which creates the perception of hearing. So it's just understandable from the centers in itself, right? So it creates a perception of hearing. So there are several ways by which you tell something is louder than the other. So loudness is one such term that you relate to sound. Okay. But can it actually be like measured? Can you like weigh it on a scale? Can you like bring it on a standard level? No. Okay, because loudness is depends on the perception. Okay. So it depends from one person to another. Okay. But so that's why we have something called as intensity. We'll be learning about that in a while now. So in case of sound waves, you have your crest, which is your topmost part, and then trough, which is your bottommost part. And then the difference between your two crests or your two troughs is your wavelength. And then from the level of reference to the top of your crest or your trough, it is your amplitude. Okay, so the more the amplitude, more loud is it. Okay, loud the sound is. Okay. So, like, in general, in this chapter throughout, we'll be actually interchanging and using the words loud and intensity together. But you might have to understand that it is not really the same. Okay. So, basic of sound is a mechanical disturbance from a state of equilibrium that propagates through an elastic material medium. So, initially, it is just all still and stuff, right? Only when there is some amount of disturbance does a sound wave gets generated. Okay, that is what they're trying to tell. And then, okay, this is something that you can know, like just as a thing. So based on the frequency, the sound is divided into three. So infrasonics is less than 20 hertz, sonics is 20 hertz to 20 kilohertz, and ultrasonics is greater than 20 kilohertz. They can just ask you this test, I don't know, too much, and ask you to like list down the examples also, or they can ask you the difference between music and noise. Okay, I think it's here right here. This one thing can be a two mark question, but yeah. So music, the difference between music and noise is something very important. So music now is pleasant to our ears. Noise is unpleasant to our ears. You just read it as a comparative study. I think it's all general knowledge. That's general knowledge. So there is regularity in the shape of the curve, and here there is irregularity. Okay. And then there is a definite periodicity. So if you see in the graph over here, it continues at a regular period. Okay. But if you see here, there is no periodicity. It's just a random noise. Okay. So, and then sudden changes in intensities are present, and there are, okay, sorry, there are sudden changes in intensities are absent over here because it's all smooth. Okay, here there are multiple sudden changes. So, just know that it is pleasant, unpleasant, regularity in the shape, and then irregularity, periodicity, and non-periodic, and then there's no sudden changes in the intensity. So these are the points that you should remember, and then you can draw that. And one thing that I would say, just for anything and everything, you can draw a diagram. That would be really nice. Okay, just to draw diagrams for everything. Okay. So, and as I said before, loudness and intensity. So often we just think that it is one and the same, but loudness is essentially is a physiological quantity. So it's just based on the perception. It's not something that you can measure as such. But intensity is just the equivalent of loudness, but it is measurable. It's a physical quantity. It is measured in watt per meter square. Okay. So, and then loudness, we all know that it is proportional to amplitude square. And then loudness is inversely proportional to distance square. So, the more, the longer the wave travels, less loud it becomes. Okay. So, it's inversely proportional in that sense. So yeah, the same thing. Okay, now intensity. Okay, so intensity we told that it's measurable, right? So what is intensity essentially? It is power by area, right? So power by area, na? Power is E by T, and area. So you just write it like that. And then for E, your SI unit is joule, and then for area it's meter square, and time it is second. And then joule per second is watt. So you write like this. Okay. You can just intuitively know, you can, even if you forget all of the formulas, power by area, you can just derive the formula and then get a unit method. Okay. So minimum sound that you can hear is 10 to the power minus 12 watt per meter square. Okay. And as I said before, loudness. Okay. Signify how far and to what extent the sound is audible. So it's again a subjective perception. Okay. So it depends on the sensitivity of the ear and how different people perceive the sound. How different people perceive the same sound differently. Okay, this is what loudness essentially is. Okay, so loudness is basically the intensity corrected by the ear's response. Okay, so it's perceived based on the ear's response. Okay, but intensity on the other hand is the physical quantity and does not depend on the listener. It is not depending on any perception aspect. Okay, so that's all. Next comes pitch. Okay. So pitch is again similar thing as loudness and intensity. Pitch is the physiological quantity. So there's high pitch, low pitch, all of that. Okay. So but the frequency is the physical quantity and it is measurable. So you pitch is essentially the perception of sound that correlates to frequency of sound wave. So the pitch is based on the frequency. So I mean, if the graph is more compact in nature, then it's a still voice. And if it's aware, if it's like widely spread out, then it's not so sterilized. Okay, so that's it about that. So if you, I think it's just know the definition for this, like all of it, intensity, loudness, pitch, frequency. Maybe they can ask you just tell, explain frequency and pitch and loudness and intensity like that. So yeah, and as I told you, pitch is directly proportional to frequency. Okay, so our ear identifies frequency with a resolution of 2 hertz. Okay. Now, is the this is something very important. Weber-Fechner law. Okay. So, what does Weber-Fechner law convey? Okay. So, this they can ask you. as a 10 mark also. So for every chapter, they'll ask you like this or that as a 10 mark. Like any one question you can choose from one chapter and right. So this you can start with what an intensity is, what loudness is, and maybe do this. But I just it's a very interesting story on how this actually started. Okay, so what was the experimental observation was that they actually closed someone's eyes and then they kept some 100 grams of weight on their hand. Okay, and then they started adding. They didn't tell that person that they're adding more. First, the person was informed that 100 grams is there and it has been kept on hand. Then extra was added, like extra on top of the 100 grams, extra 5 grams was keep on being added. Till one point, the added 5 grams was not noticeable by the person. Okay, wow. But after a point, it was slightly noticeable. Like with the eyes closed, it was slightly noticeable. Okay. So and then like they started from 100, now they increased it to 200, then they added. So in 200, then it took a slightly longer while to uh, detect that there is some increase in the weight effect. So what they're essentially trying to tell is that it relates human perception to any physical stimulus. Okay, so any physical stimulus. So here I gave an example of a weight that relates to the human perception. Okay, so that is essentially what the Weber-Fechner law is. But I don't think you need to write all of this story. Just understand so that you can adapt an exam. So instantaneous change in perception is directly proportional to change in stimulus. So I told the change in stimulus is the extra that weight that we are adding, no? So in total, the change in perception will be proportional to the change in the stimulus by your initial stimulus. Okay, and your proportionality constant is k. And now you integrate it, you will get p is equal to k ln s plus c. Okay, so when the perception is zero, that is, I was telling you that at one point, when even when the weight is getting added, there is no perception. Like they didn't perceive that the weight is getting added. Okay, so that when that you put p is equal to zero, then if you rearrange, you'll get p is equal to minus k ln s naught. So it is considering s naught is stimulus. So you just substitute this in this formula. So you'll get this one. So ln s by s naught. So it is just stimulus. So if you it is in a general formula, t is equal to k log s by s naught. But when you're talking in terms instead of the weight, if you're talking in terms of loudness, so and hence the intensity which is measurable, they will write it as I by I. Okay, it's all you can just understand all of this. Okay, nothing to memorize as such. So this is the Weber-Fechner law. But now, if you apply the Weber-Fechner law to the sound, okay, so if you apply to the sound, that is essentially proportional to the logarithmic of relative intensity of sound. Logarithmic of relative intensity of sound, I by I naught. Okay, so the lowest intensity of sound at 1 kilohertz to which a normal human can respond is okay. Lowest intensity of sound to which a normal human can respond is 10 to the power minus 12 watt per meter square. So this is just a fact that it should know. Uh, and then this is known as the threshold of hearing and is chosen as the zero or standard intensity. So I'll be coming back to what this is essentially. So this is the formula that you should be knowing. Even if you don't know, you can just derive based on the fact that your change in perception is proportional to the change in stimulus by the original stimulus. Okay, so you just integrate, put perception equal to zero, then you get your answer. Okay, so that is your Weber-Fechner law. That's really important. So it's the same thing. Okay, so now that we Earlier we saw in terms of decibel, no. Now we'll see in terms of bell. So one bell is 10 decibel. Okay, so intensity level in decibel is 10 log I by I naught dB. Okay, so that's it. And then when you talk in terms of pressures, I don't know how. I think 1 second. Okay, I think we'll see that later maybe. Nothing much. It will be 20 log P by P naught decimal. That's all. That will be in terms of your pressure. Okay. So here, what does one decimal exactly mean? Is what they're seeing here. Okay. So in the intensity level, they're substituting 1 decibel, and then they're actually finding your anti-log, and then they're hence finding this. So it tells that 1 dB intensity level implies a 26% change in intensity. Okay, so that is good. Okay, the intensity level. So we did see that their lowest intensity level is 10 to the power minus 12, no? So if you substitute that, then it will be log 1, which is 0. So that is your lowest that you can get to. And then your threshold of pain is 120 dB. Okay, when will you get 120 dB? When your I is 1. Okay, so that's okay, it's given here. Your threshold of pain is 120 dB. So it ranges from 0 to 120 dB. And then just have a take a note of it. Just know what it is. Frequency, the minimum is 20 to 20 kilohertz. So you see the first rate. Sonic. Okay. So intensity is 10 to the power minus 12. We saw the minimum. And the maximum is still 10. Pressure is 20 micropascal to 200 pascal. Okay. So the threshold values change over the lifespan of the period based on the aging and misuse. I remember them asking this one line of like one some 2 marks. Okay. Now they're finding, okay, now let's look the intensity, let it be x now. Then if the intensity is double, how much will the intensity level change? Is the question right now. Okay. So 1 second. Okay. So how much will the intensity level change? Is the question right now. So how will you see? So instead of x, you substitute 2x. And then you do mu minus O. So you essentially divide this, no? So 2x by I naught divided by x by I naught, which is 2. Okay. So that will be 3, approximately 3 dB. Okay. So the new intensity level increases by 3 dB. That's all that this is. Okay. So now maybe this question is difficult. Okay, what does 0 dB mean now? You can, in your formula, instead of your original IL, you can just substitute D, it's 0. And then you perform all of your log and your what, okay, wait, if you get 0, if you put 0 over here, 0 is equal to 10 log I by I naught. Okay, so let's have it as I by I naught. So it will be 10 pi 0 is equal to I by I naught. 1 second. So 0 is equal to I by I naught. So your I by I naught will be 10 to the power 0, right? So then I by I naught will be essentially 1. And then if you rearrange, it will be I is equal to I naught. But what is I naught? Your lowest threshold of I naught is 10 to the power minus 12. Don't forget your SI units, watt per meter square. In the part. And then for your second question, mosquito produces the intensity level of 0 dB. If 100 mosquitoes are present, okay, what will be the intensity level? Hmm. Okay. So they're telling us that there are 100 mosquitoes present. So what will be the intensity, new intensity level? Okay. So essentially, okay. Oh, okay. Okay, so essentially, your intensity level is 10 log. Instead of I by I naught, it's 100 I naught by I. Okay, so it's any times. You're telling it is 100 times. Okay, so your end is 100 over here. So it will be 100 I naught by I naught. Okay, so your I naught and I naught will get cancelled. So it will be 10 log 100 I naught by I naught, which is essentially 100. Oh, sorry, I think screenshot turned off. I will share it to you. Okay, thank you, Hari. Okay, so 10 log, 100 I naught by I naught, which is 100. So what is this? This is 10 square. So 20, what is asked for? dB. Okay, so for the intensity level, it is dB. Your intensity is watt per meter square. Don't forget. And then another question. A machine produces a sound intensity level of 70 dB. If an operating in a room with a sound level of 80 dB, what is the total intensity level within the room? So the intensity level, okay, there's given out here. So intensity level, uh, one which is 70 dB, and then the other one is 20 dB. So you equate this formula. 10 log I1 by I0 is equal to 70, 10 log I1 by I0 is equal to 80. Okay. So you perform all of your logarithmic operations. Then you will end up with these two. So when it comes to these questions, just know what are they giving the question and what to decide. With that, I think it's pretty easy to substitute the formulas and that's all. So yeah, they're asking your total. Okay. So the sum of it, if you do, it will be I1 plus I2 by I0 is 10 power 7 plus 10 power 8. This 10 power 7 is 10 power 8. So again, rearrange. So you're getting this, the sum we are getting as this. Okay. So, so if you substitute, actually, I think it is I1, I1 plus I2 is this value, right? Then your I naught is 10 to the power minus 12. Okay, am I right? So your I1 plus I2 is actually 1.1 into 10 to the power minus 4. So how are we actually getting this? We shouldn't get confused. Okay. So 1.1 into 10 to the power minus 4. Okay. By your I0, we know that the threshold value is 10 to the power minus 12. So you'll end up getting 1.1 into 10 to the power 8. Okay. That's all. So you just substitute that value and then you 10 log 1.1 into 10 to the power 8. We will get 80.41 GB. So that's our answer. Okay. So all of this sensitivity is shown here. This is not definitely needed. If you want, you can just skim through, but you won't be tested much on this. Um, okay, I already told you, right? So your intensity is proportional to uh, pressure square. Okay. So all of this, I told you in terms of, we already saw in terms of I by N. So 10 log I by N. Okay. If it is decibel, in decibel. And then for in terms of pressure, so when the intensity to this in terms of pressure is 20 log P by T. That's all. And then your threshold is uh, 2 into 10 to the power minus 5 or 20 micro Newton per meter square. Know your know all of your SI units very well. Okay. So loudness of a sound depends on the frequency of the sound and the sensitivity of the ear. That's something that you already know. Saying that two sounds are equal intensity is not the same thing as saying equal loudness. So I told you that we sometimes do interchange the words we use in daily life, but it is not really the same. You can't really interchange and use at all times. Therefore, two different 60 decibel sound will not in general have the same loudness. So we'll now be looking into something called as the equal loudness curve. Okay. So this you will definitely get as one of your 10 marks for your last detailed question. So this is something that you need to know very detailed. So every single point you might have to know. Okay. So what is your equal loudness curve? So it tells a relationship between with increase in intensity, how does the frequency changes and how we actually perceive it. Okay, so the loudness curve captures the frequency response to our ears and its variation with intensity with the increase in intensity. With the increase in intensity, how exactly does humans perceive these frequencies? Okay, so this is what the loudness curves talk about. So our human ears are actually sensitive to uh, one 1 to 4 kilohertz, so around this region. Okay, so it is sensitive around this region, so that's why we see a dip over here. So this is due to the resonance of our auditory channel, our ears auditory channel. So because of that, there is a dip over here. Okay, so equal sensitivity to all frequencies. So if you see here, at very high intensity, at like 100, 121, right? All of them, after a particular point, anything and everything is just considered as the same perception level for a human being. Okay, so that is what the equal loudness curve talk about. So you have to ensure that you write all of these points. Okay, so the ear is less sensitive to lower frequencies, and and this discrimination against low becomes cheaper for softer sounds. Okay, so if you see here, when the frequency is lower, it's less sensitive. Okay, so the curve represent equal loudness as perceived by the younger. It's just all same points repeated over and over again, but you ensure that you write all of this. And then I told you that the dip is because of the resonance of the auditory canal around You can either write 1 to 4 kilohertz, but it's specifically 3 to 4 kilohertz. So that's all with respect to equal loudness curve. But uh, since this will be asked as a 10 mark, when it comes to writing it as an answer, you have to write all of these points, this diagram, and all of these points in the diagram. And then if you can just add a few on example, like giving an example on how this actually works. Okay. So maybe you can see this can see the response to very loud sound is much flatter. Okay, so very loud sound it is much flatter. Okay, that's what it is. And then it's almost perceived as the same sound throughout. Okay, after a particular point, everything is one and the same. Okay, and then the curve dips between 2000 to 5000 kilohertz. This is what I said. That implies that less sound intensity is necessary for the ear to perceive the same loudness as 120 dB, 100 hertz tone. So, since your ear is highly efficient over here at this region, a less sound is enough for you to perceive a sound that is even higher. Okay, that is what they're telling over here. That's all. So, you just, these are just different, uh, if you see this here, equal loudness line at 64 tones. So, all of this is just the same sound, essentially. Okay, and coincidentally, if you see here, at 1000 hertz, they're meeting at 65 intensity. Okay, so just a diagrammatic representation of how you interpret between your sound intensity and your frequency. Okay, that's all. Okay, so maybe we can look into this. A tone at 60 hertz has to be played at what decibel to produce the equal perception or that of 1 kilohertz at 20. Okay, so at 1 kilohertz at 20. Okay, so for 60 hertz, so you have to find where 60 hertz is. 1, 2, 3, 4, 5, 1 second. So this 1000 is this part. Okay, so 1 kilohertz at 20 decibel. So 1 kilohertz at 20 decibel. And then there's 60 hertz. So you found 60 hertz. So they're asking how much decibel should it be so that the perception is same. Okay. So if you see, I told you that this curve, no, it's all of equal loudness. So you just see where it meets. Okay. So it meets at here. This line and this part meets at here. So at 60 dB, okay. So at 60 dB, this perception is the same. Okay. So that's all with the first one. Then your pressure of the tone at 70 hertz should be, okay, let me clear all of this. Okay. The pressure of the tone at 70 hertz should be dash times 4 to produce a perception equal to that of 1 kilohertz at 100 decibel. Okay. For this, you have to do that similar to the question that we did before. So essentially, they're talking in terms of pressure. So what formula should we use? We have to use that formula where 20 log T by T naught. Okay. So your T is unknown. That is we have to find the P at 1 kilohertz. Okay, so the P at 1 kilohertz by P naught. So P naught, you know the value for it, 20 micropascals. No, so is equal to 100 is what we will write. So I'll just write and show you. So 20, um, oh, very delicious. Okay. 20 log P by P naught. So P we actually don't know. P naught we actually know that it is 20 micropascal or 2 into 10 to the power minus, whatever you, okay, is equal to 100 is what they have given, right? In the question they have given 100 decibel. Again, you rearrange, you solve this, you do everything. That is one. And then they've given you 70 hertz. It's equal to 70 hertz is what they've shown at 70 hertz. Pressure of the tone 70 hertz should be dash times 4. Okay. So again, we have 70 is equal to, you write this same old thing. But 70 is hertz, you can't really write that. Okay, so then at 1 kilohertz, it's actually 100 decibels. Okay, so 100 decibels. So 100 decibels is essentially your 100 phone on 100 phone. Okay, so that thing. So for 70 hertz, so it will be somewhere around 100, 90, 80, 70. So this line, how much time will it be more? That's what they're asking. No. So if you go up, you see where it meets. Essentially 110. In this 110 it meets. Okay. So you actually put here 110. Okay. So it's same thing, right? 20 log P by 20 micropascal. So that's all. Then you actually subtract this is 100 and this 110. No? So you subtract this is equation 2 and this is equation 1. No? You just subtract 2 and 1. You solve everything. You will get how many times one is more than the other. Okay, that's all. Okay. So next one. The difference in dBSPI between the tones 80 hertz and 40 hertz that are just audible is. Okay. So that are just audible. So what do you mean by just audible? So that is your threshold. Just to know that just audible is the threshold is the way that you can actually hear. Below that you can't hear. So above that obviously you can hear. So this is what they mean by just audible. Okay. So what are they telling now? So you just have to be comfortable with the mapping. They're mostly do the same diagrams. So map map it properly and then you can figure out. So 80 hertz, 190, 80. Okay, and then here 40 hertz. 20, 30, 40. Okay. So this is essentially from 50. Yeah? What is it? So it's 10, how is 10? Okay. 10, 20, 30, 40. This is 50. And this one is 30. See, whatever you map it, whatever you get it, that's all. So the difference in it is 50 by see, 50 minus 30, 20, that's all. Okay. So I hope this part is clear. So this is something that we will tested on definitely. Like what is equal on the curve could be a definite 10 mark question. Just have everything, be clear with that, and how you apply it also. Okay, so many sounds were played at the same time. It's easy to hear and identify different instruments. Uh, okay, how do we choose the separation? We use our auditory fillers to separate different sounds from different things. Okay, so all of this is not necessary. I'm just skipping all of the unnecessary parts. Oh, okay, so much is there, but not like, and this also. Okay, this I think we can cover. Okay, so if there are two sounds close in frequency, and one of them is very high intensity, it will saturate the cilia and therefore mask the lower intensity frequency. Let's say you have two sounds with similar frequency range, okay, similar frequency, but one thing is more loud. I mean, okay, as I again said, loudness and intensity, I interchangeably use it interchangeably, but essentially intensity. Okay, so one of it is more intense than the other. That means the more intense level wave will actually mask the least intensity. No, that's what they're saying. That's all. That's we already know that. So, and then other, if a set of celia corresponding to one band is simultaneously excited by two frequencies within its bandwidth, as indicated by two red lines, or A and B in the example on top, they will not be resolved accurately. Okay, so with same frequency level, you can't really distinguish between them. It can be resolved accurately. So any noise, external noise contribution within this band will also reduce the perception of the signal. Already the perception is not really clear. Okay, if the intensity is more, then of course that will mask the other one. But if let's say if it's both similar frequency levels, there's definitely some amount of noise that's getting masked. Okay, so even if there's more external noise also, then it adds up more to the mask. So, so we need noise cancellation to actually improve the signal detection within the sound. So external, you need to cancel out the external noise detection. So that's why we need the noise cancellation. That's all, just a simple thing. Okay. Uh, okay. Now we'll talk about timber. Because everything fine till now. You can react maybe. Uh, okay. Just tell me if I need to go a bit fast also. So yeah. Now timber. So sounds are generally categorized by pitch, loudness, and quality. Okay, so the sound quality of timber describes those characteristics of sound. It allows the ear to distinguish sounds which have the same pitch and loudness. So, what is the differentiating factor when it comes to the same pitch and loudness? Okay, same pitch, na, same frequency that we follow. And then with same pitch, same loudness also, what is the differentiating factor? So, the sound quality of the timber is the differentiating factor. So it's mainly determined by the harmonic content of the sound. Okay. So it's based on the vibrato and the attack decay envelope. So this is something that you need to keep in mind. Just see whether it's mentioned. Okay, I don't think it's okay. Okay, the two sounds with same loudness and same pitch, but from different instruments. Okay, so violin and flute. So The amplitude is same, not same loudness that you already know. Not you have the graph, your amplitude is more or less the same, now, then same loudness. Then if it's frequency same pitch, okay, that you already know. But the waveforms are actually different. Okay, for violin and your flute, your vibrato and your attack decay could actually go. I think there will be definitions given for all of this. We will be covering it soon. Just skipping off all of the unwanted parts, mostly called pictures. Okay. So our ears are very good at perceiving different sounds. So one way to do is through the timbre of the sound. That's how we differentiate between different instruments actually. Okay. So timbre is the tonal quality or the tonal color of the sound. So it's determined by the overtone and harmonic of the sound produced. It's based on the harmonic content. So you have to know what your definitions for your harmonic content, your attack decay, and your vibrato. Okay. So the amplitude and pitch change in each harmonic gives the instrument their particular timbre. So the amplitude and the pitch change in each harmonic. In general, your amplitude and pitch is same, okay? But each harmonic it differs by slight bit. That's how you're able to like differentiate between a flute and a guitar. You can easily determine, no? So the quality of a sound is as much as perceptual phenomenon as it is a physical one. So it also depends on your perception. That's all. Okay. Based on the perceptual capabilities of the ear. Depending on perception, you perceive something more different than the other. Uh, okay, the primary contributors I told you for the timbre of the sound is your harmonic content, the number and relative intensity of the upper harmonic present in the sound. Okay, so some musical sound sources have overtones which are not harmonics of the sound fundamentally. Actually, all you have to know is what exactly is the differentiating factor, and that is your timbre. So the timbre, you are differentiating it based on your harmonic content. That's all that you need to know. There is like a lot of stories written on here. So while there is some efficiency in categorizing such sources in terms of their overtone, it is always possible to characterize a periodic waveform in terms of harmonics. Okay, so this is called a Fourier analysis. So what in Fourier analysis, these harmonic contents, no, they actually sandwich it. So the harmonic content determines the waveform of the sound signal when displayed as a function of time. Okay, when the same harmonic content which is displayed as a function of time, so it is made into a frequency plot. Okay, so this is essentially a Fourier transform. Okay, so Fourier transform is a concept that's used in anything and everything of physics. Okay, so anything and everything, the essence comes from Fourier transform. So that's up with this. There's this supercomposition of all of the harmonic content, and then you get your Fourier transform. So much content. With all of this is not needed. So, as I said before, to just get a better visual representation. So this is your Y1, your sine wave, Y2, Y3, all of this, just supercomposing it, and then you get your final output. Okay. So, so what is your Fourier transform? Any time domain periodic signal can be expressed in the series of sine and cos functions. Okay. So it is time dependent, I told you before, right? So it was represented in based on time, as a function of time. So displayed as a function of time. Okay. So that can be expressed in a series of sine and cos functions. Okay, so this spectral distribution is called as the Fourier transform. So this definition you might have to know. And this graph also I showed you before, right? Earlier that graph had a time in the x-axis and it has been changed to frequency. Okay, so that is how you represent it, intensity by frequency. This is also, I mean, same thing for the equal level curve also. So the tone quality is based on the amplitudes of the harmonics. Okay, so easier way to look at the amplitudes of harmonics is through your Fourier spectrum, or your Fourier transform. Not necessary. All of this you can just see what it is, but not necessary. Just sound wave for piano, violin, and French horn. Okay, attack time. Okay, the duration of note takes to reach its maximum intensity after being played. So once something is played, what is the time till which it reaches its maximum intensity? After that, it stays still for a while and then it starts decaying. So any and every sound starts decaying, right? It won't be ringing continuously. So that this is the attack period, and then the sustaining period is your sustain time, and then the decay period is the decay time. That's all. These are just examples. Short attack time, no? Your piano, guitar, to immediately string it. Then the attack time, the time for which it reaches its maximum, it immediately reaches its maximum intensity and it starts sustaining and then decaying later. Did anyone stop? Okay, never mind. So yeah, similarly, some examples is listed over here. Now again, before we saw it, first we saw harmonic content. Now this attack and decay. So based on this attack and decay also, you tend to differentiate what is what. Like you differentiate between a flute and a guitar, all of that, right? So based on the attack and decay also. So they're just telling the same thing again and again. Uh, the decay is long and gradual by comparison. Another contributes to the quality of timbre is the attack and decay. So here they're given a guitar attack and decay. What are stories I told here? Essentially, these 3 points is what you need to convey over here. Okay. So these are just generalized points that they're given. So you are sensitive to these attack and decay rates and very able to use them to identify the instrument. As I said before. So this attack and decay with the help of it, this is your another differentiating factor for finding a sound which has equal same pitch and like intensity. And yeah, finally vibrato and tremolo. So it's periodic changes in the pitch of the tone. Okay, how the pitch changes with respect to time is your vibrato. Okay, so this talks in terms of your frequency. Okay, and your terminal periodic changes in your amplitude or your intensity. I mean, loudness. Okay, I'm essentially highlighting everything, but you need to know this. Okay, so this your definitions for your harmonic content, vibrato terminal, and what is that between you need to know. So vibrato now talks with respect to your pitch or your frequency. Periodic changes in your pitch. Terminal periodic changes in your amplitude or loudness. Okay, and this is another factor by which you'll be able to distinguish between different sounds. So vibrato of your Singer's voice uh, it aids significantly in distinguishing the voice from other musical sounds. That's all. So just make you know that vibrato in terms of frequency, change of frequency, and switch of frequency, tremolo is change in loudness or amplitude. And yes, the same thing just put in one slide. Uh, so, okay, the quality of timber is a characteristic. I think this is sufficient when they ask for a 2 mark. Otherwise, if you need to elaborate it, you can just always draw a diagram and elaborate. So yeah, attack decay, the temporal variation in the amplitude of sound. Okay, especially at the beginning and the end of the sound. So at the beginning it's attack, at the end of the sound it's decay. The temporal variation. Variation in amplitude in the beginning and the end. That is your attack decay. Vibrato, I told you it's temporal variation frequency. Turbulent, it's temporal variation in your amplitude. Okay. Harmonic content, the relative intensity and space among overtones. That's all. So attack na how the sound is created, decay na how it terminates. Okay, that's how a sound is created and how it terminates. Again, to give a brief, attack is a temporal variation in the beginning of amplitude of sound in the beginning. Decay is temporal variation of amplitude of sound in the end. Verbato, vibrato, I've been telling verbato, I'm sorry, it's vibrato. Vibrato is temporal variation in frequency, terminal is temporal variation in amplitude. The harmonic content, relative intensity, and phase among overtones. Okay, that's all. So vibrato, terminal, you sustained E, the E sound, so that modulate, amplitude modulation of sustained E. And then vibrato, the chirping sound, okay. Instantaneous change in frequency. So you see words chirping. Okay. I think this part is done. Okay, so we'll look at this question. Which of the following parameters categorize timber? Okay, frequency. Okay, attack decay, vibrato harmonic content. Method. Spectral distribution is dash of time domain sequence. I think some frequency representation, like, how do I put this? Spectral distribution is dash of time domain sequence. The frequency representation of time domain sequence. And then state if the following statement is true or false. Yeah, this essentially I told you, right? Your time will be here and you represent terms of frequency. I'm writing first, but yeah, you represent terms of frequency, that is your spectral distribution. I think here is fill in the blanks, however you can write, put it in that will work. State if the following statement is true or false. Okay. Certain musical instruments can produce a pure tone. Okay, there's nothing called as a pure tone. Okay. So only I think a tuning fork or something that gives like a very pure tone. But ideally there's nothing that exists. Okay, like real world there doesn't exist an ideal pure tone, no? So that's why nothing has to exist. Okay, this is something I've already seen. I think it's time we skip a lot now. Okay, yeah. Okay, now general methods for ultrasonic generation. So there are three methods. Okay. So now from now on, I think all of this is uh, slightly important. Okay. So just you need to know everything as a question. If they ask you the question, just know what to write and what to draw. What are the main things that you have to write? Okay. So first, it's your Galton's resistance. Okay. So when blown at high pressure, an incident on a scatterer triggers oscillations in the cavity. So adjusting pressure and the distance to the scatterer. So essentially what it means is that okay, okay, if you blow your whistle at the high pressure, then it starts triggering the oscillations in the cavity. So inside the cavity, it starts triggering the oscillations. So what you can adjust is you can adjust your pressure based on your pressure, based on how much the air blown. Okay, that you can control, and the distance to the scatterer. You can actually try to match the frequency to that of the resonance frequency of the cavity. Okay, so that's all. This humming sound of transformers because of magnetostriction. So we look into what that is now. So this is something that's very important. Uh, yeah. Okay. Now, when a ferromagnetic rod is subjected to magnetic field, okay, it undergoes a change in dimension. So when it so essentially your length expands. Okay. So if you see here, it's all scattered and then it's slightly elongated. Okay. I think it's mentioned here properly. So in your magnetostriction has to provide magnetic field L plus delta L. Okay, so it's slightly along it. The length increases by 1 by this much to 1. It is just a small amount, okay, upon magnetization. Okay, so so this is that it undergoes a change in the dimension. So you just need to know what is what so that you can actually write it on your own also. So when a ferromagnet rod is put into an magnetic field, it undergoes a change in the dimension, mainly the length. So the length increases. So this change is proportional to the strength of the magnetic field. So your change in length depends on the strength of the magnetic field, and it is independent of the orientation or the sign, whether it's north, south, or that doesn't matter. So this is called as magnetic field. Similarly, we learning a lot of concepts. Mathematical friction is one of your applications uh, for generating your ultrasonic generator. And magnetical friction, it involves some amount of magnetic field. Okay. So what are you doing? You are having a ferromagnet. You are it's subjected to magnetic field. Your length expands. And as I told you, your length, your change in length is proportional to the strength of your magnetic field. B is your magnetic field. It has to be bar, be like this. But okay, that's never made like matter. Pushes the medium in contact with its initiating pressure range. So as this elongates, there is some amount of pressure that's created. Okay. So the change in shape subsequent to magnetization or demagnetization occurs very fast, the lag time being less than 1 microsecond. So as if you apply magnetic field, then it comes. Then if you don't apply it, it again comes back. So there's not much lag time with this happening. Okay. So yeah, a ferromagnet rod stays inside a coil carrying alternating current. Again, it is suffers same change in length. There will be a change in length. And this theme is like the surface, so figuring out what is essentially needed for exam. Otherwise, you could just cover everything for like 4 5 hours. Uh, I don't think all of this is essential. So next comes your ultrasonic generator. Is everything fine till now? Like, please look at the chat. I'm sorry. You can react if it's fine. Okay, and move on. Okay, so your ultrasonic generator. So I were to say then this is mainly the thing that is required. Okay, so decide the frequency of the wave to be generated and then generate magnetic field of varying at the frequency f, generating a current varying at the required reference frequency f, generating a time varying magnetic field using this. So this okay. So this something happens. Okay. Sorry for the disturbance. Okay, so ultrasonic generator. So what does it has to give you your ultrasonic waves. No. So ultrasonic waves are above 20 kilohertz now, you already know that. So here, previously magnetic friction, what did we see? We saw that when there is magnetic field, then the length expands. Okay. So and there's some amount of pressure that's created, and then there's like some amount of vibration that produces ultrasonic waves. That's what we saw before in magnetic friction. Now here, you have to first decide on what frequency do you want. Like finally, after you're performing this, at what frequency your ultrasonic wave should be. Okay, so that is something that you should decide in advance. Uh, then you generate magnetic field according to that. Okay, so you generate a magnetic field based on the frequency that you need. So generating a current varying at the required reference frequency F, okay, and generating a time varying magnetic field using it. So based on the frequency that you might need, you generate the respective magnetic field. Okay. So choose a magnetic material of appropriate length so that the reference frequency matches that. Okay. So you need to choose your uh, magnetic material properly. So this F rod no. This frequency is equal to 1 by 12 into root of the Young's modulus E by density. Okay, rho. This you can note it down. Okay, so place the appropriately magnetic material in a field and then ultrasonic waves of F will be generated. That's all. So under this diagram, you have to also know. I think it's base emitter, collector, all of that basic things. I'm sure you mentioned. When it is AC, then this is the formula. Okay, then as I said, you when it's alternative current of frequency, then FFE is 1 by 2 pi root LC. Otherwise, this is the thing. I think not much is required on here. Just know your diagrams well. Just understand the gist of it. Why is it used for? Okay, so you decide on a frequency. Based on the frequency, you generate your magnetic field. You choose your appropriate magnetic material, and hence you generate your ultrasonic waves of frequency of generated. Okay, that's all that you need to know. Okay, so what are the advantages of it? The circuit is simple. Uh, Large output power resources. And then alloys such as nickel and ferrite. So all of that ferromagnetic material we saw about the that is your magnetostrictive material, no? That and all is made up of nickels and ferrite. So all of this is easily available, very easily available. So not much of a disadvantage. But the problem, the disadvantages again. So you need to know your advantages and disadvantages for this. So it can generate only up to 3 megahertz. Okay, so it can't go more than that. And then output frequency drift with temperature. Drift with temperature. Then your bandwidth of the resonance changes with the degree of magnetization. So there is change with respect to temperature. Your E which varies with the degree of magnetization and the temperature. So your E also varies, your magnetization also varies, your temperature also varies. Can you hear me? Yes, so my chat or something. I feel like there's something. Okay, I'm assuming you can hear me. So that's all with this. You need to know that it can generate only less than. I think I left the meeting. So give a gist about this. Your ultrasonic generated principle. You decide on the frequency. You hence decide on the magnetic field that you require to generate that frequency, and then you choose your appropriate magnetic material. Usually, it involves nickel and ferrite, which is commonly available. So that is your advantage also. So hence you generate your ultrasonic waves of frequency. Okay. So the advantages is that the circuit is simple, large output power, nickel and ferrite are easily available. And then here disadvantages, you can only generate up to 3 megahertz and output frequency just with temperature. And even your degree of magnetization, your bandwidth of resonance changes with the degree of magnetization. The degree of magnetization, uh, it actually relates to your temperature and your density, which density, okay, density always varies with temperature, no? So that's it. Okay, now comes the next important thing, that is piezoelectric effect. So this is something that's really important. Uh, so essentially, what is this? Okay, so when one pair of opposite faces of certain crystals like quartz is subjected to pressure. So here, if you see the picture also, when it is subjected to pressure, the other pair of the opposite faces develop equal and opposite charges. Okay, Here, if you see, there's a pressure that is being built, they're pushed inwards, and the opposite part, it gets opposite poles, plus positive and negative poles. Okay, so instead of pressure, if tension is applied, the sign of the charge is reversed. The converse is also true. So if tension is applied instead of pressure, then the sign reverses. If you see here, earlier it was plus minus, here it's minus plus. Okay. So the alternating voltage is applied to one pair of the faces. The other pair of the faces elongate and contract alternatingly, producing oscillation. Okay. If there is an alternating voltage, if there is an AC voltage, then the faces keeps contracting and relaxing. So it essentially produces an oscillation. Okay. So this formula you have to remember. It's the same thing that we saw before, no? F is equal to 1 by 12 E by rho. That's all. The material which converts one form of signal into another is called as transducer. So examples are what your ADP, all of that, process, all that. So here there is no step. Once they apply tension, it expands. And once they apply pressure, then it contracts. So this continuous contraction and relaxation causes your oscillation. Okay. Okay. This I think that is more understandable. So refers piezoelectric effects refers to the development of EMF across the opposite parts of spaces of asymmetric crystals and application of mechanical stress. Okay. So when you apply some pressure, to see here, when you apply some pressure, tension, then there's continuous relaxation and I mean this is your application of mechanical stress, the tension that you're applying. So there's opposite pairs, as you saw, opposite poles generated. So this produces an EMF. So this EMF appears to be perpendicular to the pair of faces. Okay. Uh, and this is reversible. Okay. This is not irreversible. This is reversible. So this is what you looked at. Piezoelectric is this. So your inverse piezoelectric effect, that is your vice versa, that is what provides your it generates your ultrasonic waves. Okay. Okay. A piezoelectric crystal has to be first cut and shaped before usage. The natural quartz is a hexagonal bipyramidal. Okay. This just after you explain what piezoelectric effect is, this is also they could expect as one of your questions. Um, you just need to know what X cut and Y cut is. Just draw this example, and then if it is cut from diagonally, it joins diagonally, then it is your electrical axis. It is cut like this with your sides, then it's your Y, your mechanical axis. That's all. So this construction and all is not required. So this diagram is something that you might have to learn. Piezoelectric generator, I think we've already discussed these formulas. Okay, so merits again. So before we saw that it only generates up to 3 megahertz. But here if you see the merits itself, till 500 megahertz of ultrasonic waves can be generated. Okay, and it is not affected by temperature. Earlier it was affected by temperature. Correct? No. Just you can do a comparative study so that you don't forget all of the points. Then a range of the frequency can be obtained by using different transducers. Okay, so this range of frequencies can be obtained. Mm, so here it can generate the gigahertz, stable frequency. Demerits are polishing and cutting. Okay, so here if you see, I told you that your piezoelectric crystals has to be polished. Is it Piezoelectric crystal has to be first cut and shaped before using it in oscillating circuit. So it has to be like perfect. So you need to like do all of the cutting and shaping process beforehand. So that is slightly more expensive, and the cutting and polishing is not really easy. So that's a big part. Okay, now uh, we saw the generation of uh, ultrasonic waves. Now we'll see detection of ultrasonic waves. Okay, so so almost all techniques of detecting are based on superposition. Okay, so based on superposition of the waves. So here, if you see, the principle that find the spacing between the nodes and the antinodes and hence determine the wavelength of the ultrasonic wave. So these are your nodes, okay, where it is densely populated. These are your nodes, and then the rest are your antinodes, okay. So these are your nodes. So between the spacing of your nodes and your antinodes, you actually find your wavelength, okay. So uh, resistance of CT wire changes at nodes and antinodes due to temperature variance. So at this node, there is some amount of temperature variance is there, and hence your resistance changes. Okay. So in Kunz tube, you see there is a reflector, there's a transducer. So only when you in your nodes, if you see there is the sand dust that is accumulated. Okay, so this is how you detect the presence of your ultrasonic waves. So if you see uh, there is in your nodes there is actually uh, okay, there is what there is in your notes there is accumulation, and here also if you see the sand, then you detect the presence of the ultrasonic waves. That's right. Sorry for a second, I forgot English. Uh, yeah. This method requires the tube to be filled with lycopodium powder. The powder sets at the bottom of the tube, and when ultrasonic waves is passed through, then only at the nodes it gets accumulated. Okay, so that's how you test the presence of your ultrasonic waves. So again, I don't think this is required. I think it's again detection with the help of meter-based sensor. You need to go in detail. You can just refer to it as points, but I don't think it's really required. Okay, now we'll be dealing with acoustic grating. So okay, by forming acoustic grating using a medium in which V is to be found, its value can be determined. Okay, let's leave all of this. So again, acoustic grating, we're going to find the presence of the ultrasonic wave. That is what we're going to do, right? So ultrasonic waves pass through the liquid and get reflected. So liquid is taken into measuring cell. A transducer is fixed at one end and a reflector at the other end. So here if you see there's a transducer and the reflector is in the other end. Okay. So ultraionic waves pass through the liquid and get reflected. Okay. Uh, at nodal planes, the density is maximum. Yeah, it was the density. Yeah. The density is the word I forgot. So the density at the nodes is the maximum. Okay, and anti-node, it is minimum. So hence you find like a black and white stripes as such. So wherever you find black, that means it is your node part, and then this white region is your anti-node part. So the density is more in your node part, and then it's less in your anti-node. This picture conveys it better. So the periodic variation in density. So if you see here, the density is high because it's a node, correct? All of these nodes, the density is higher, and in antinodes it is lower. So it forms a series of higher and lower density patterns. Okay, so this resembles diffraction grating. Okay, since the grating is formed by ultrasonic waves, it is called as acoustic grating. Okay, that's all. So detects the presence of the ultrasonic waves with the formation of alternative uh, patterns of the high and low density patterns, and this is what is called as the acoustic grating. So with this, you see diffraction of zeroth order, first order, second order, all of that, and hence it is called as your acoustic grating. Okay, so your monochromatic light, so your laser, when it passes through, it gets diffracted. So this is what your acoustic grating is. So be thorough with your diagrams and all of this. Here you will definitely be interested upon. Okay, okay, here it's given properly. D sin theta is equal to n lambda. Okay, so this is your grating equation. So if you put D is equal to lambda acoustic by 2, okay, then you will end up getting this as your lambda. Okay, in terms of your uh, wavelength for your laser. Okay, now if you need to find the velocity, no? Velocity of your ultrasonic is just mu lambda, no? So frequency into lambda, you will get your final answer. So this also, all of your formulas for acoustic rating and all of that, you need to just know it at least, so that even if not in question answers, you'll be definitely tested on other ways. Okay. Okay. Other uses of acoustic rating. All of this is not required. Okay. Then reach 200. Nice. Okay. I think we'll try to cover it up as soon as possible. Cannot travel through vacuum. Cannot travel through vacuum. And these waves travel with speed of sound in a given medium. These are just properties of ultrasonic waves. You just need to know this. There's nothing to explain as such. They are reflected and refracted just like light waves. And then the velocity remains constant in homogeneous medium. It waves travel with the speed of sound, and then their velocity mainly depends on the density and the Young's model. We previously saw the formula also, right? It was E by rho and all root of E by rho and all was there, right? That formula. So it depends on your, I think, 1 by 12 into root of E by rho. Uh, and then the speed relation is this based on the dense media. So this is less dense, speed is less like that. It goes on. So all of these points you need to remember. It can't travel through vacuum. It travels like speed of sound. Velocity remains constant in homogeneous media, and it is reflected and refracted like light waves. It travels like sound, speed of sound. It reflects and refracted just like light waves, and it depends on your Young's modulus and your rho. So the velocity is equal to 1 by 12. Okay. So principle of ultrasonic inspection. Okay, all of this is not necessary. Why is there so much? As far as I know, I didn't have this part. I don't think this is necessary. Okay, now your ultrasonic transducers. Majorly, you just need to know the types, okay? So, what is your ultrasonic transducers? They're in ultrasonic testing, the use of this thing makes the user understand, locate, and identify the flaws. So, you need to find the flaws or your cracks or your any disturbances when you're doing when you're having ultrasonic waves, no? So with ultrasonic you can actually any any flaws that is actually there. Okay. So your your types of transducers, so contact emotion add couple, normal beam, angle beam, single element, dual element. I think you'll be able to understand if you see the examples on what it is. Okay. So I'm using. Okay. So contact transducer. So just as you come in contact with the test specimen. So, okay, what are you doing? You have to test whether there is some crack that is there. Okay. So for that you will use your transducer generally. I mean, this is one of your applications for your ultrasonic transducer. So if you keep in contact with something, so that so you if you need to keep in contact so let's say this is your ultrasonic transducer, keep in contact with some other material, that means their reference frequency should match at that level. No? So the frequency between your transducer and your testing material should match. So for that, you use something called as couplant. Yeah, I think you should know the definition for what a couplant is also, but this is just like why, I mean, the use case of what the couplant, okay? So you use to something called as couplant so that you actually match the reference frequency. Okay, so I mean, if you keep it in context, you can find the cracks if it is there. And an immersion transducer operates in a scanning tank where the specimen and the transducer are fully immersed within fluid. Okay, so it's both immersed inside water. So with this, you will be able to detect any cracks or something. Okay, so air coupled transducers require a special layer of material from the pulse to the air to the sample. So there's some material that's there. So oh, the picture itself is clear. Okay, there's some material. So as it detects something, it will transfer it through this material via the pulse. I think if you can draw the basic diagram of it and explain in your own words, it will be fine. All of this just need to remember the subheadings at least. So this thing, if you remember, I think it will be fine. So contact, immersive, and air coupled that you have seen. Now it's normal beam transducers transmit a wave normal to the surface. So the beam again here also everywhere the coupling comes into picture. So you need to know. So it's just used to match the reference frequency between your testing thing and your ultrasonic transducer. So okay, here it sends the beam normally, and here it sends angularly. So mm, just the same thing it's telling again and again. So there's this angular beam that is generated, put in different words. Okay, then classification of transducers on the basis of the number of elements. So single element transducer, it contains only one active element. This often results in reduced cost and simplicity in design. So there's just one active element that is present. And in a dual transducer, there are two transducers. Okay, so they contain a separate transmitter and receiver, and then they're housed in a common case. So there are two transducers. So this arrangement improves near surface resolution because the second transducer does not need to complete a transmit function before listening for echoes. So this is something we'll be dealing with soon. Okay, so uh, with respect to echoes, all of that, your B scan, C scan, A scan, all of that. So Dual elements are commonly employed in thickness gauging of thin materials. Um, for to determine your thickness gauging of your materials is certain, so you properly use these dual element transducers. All that you know is single element and dual elements. That's all. It's two transducers that is how they are in one case. One is your transmitting crystal and other one is the receiving crystal. So that's all that we need. Um, Test techniques. Uh, I don't think this part is needed. This part was not really there for us. But okay, this you might have to know. So what is this essentially? So how much distance does the ultrasonic transducer travel? So distance is, it's speed into time, v into t, but why is there a two? Okay. So if you see here a transducer, if it detects some crack over here, it travels from here and again goes back. So it happens two times. Okay, so it is finding one part, so it's by two. That's all. So usually we'll be dealing with normal beam inspection in all of your scans. So only this is something that you need to. Okay. Now comes, I think now it's slightly more interesting. One second, let me look into what is there. Okay, I think after this it will be fine. Not much. We'll just deal with one main topic and after it's all types of scans. Okay, so your time of flight, that is the time it takes, okay, to reach at your crash. So this is your transducer, this is your shaft per se, then how much takes the time, okay. Used for detection of flaws. So partial reflections that arise at discontinuities in the medium is used for detecting and estimating depth at. So once you actually notice the crack, you transmit it, you notice the crack, and then you reflect it, right? So there's some amount which is getting transmitted otherwise also, but there's partial reflection over here, correct? No? So this, what does this partial reflection convey? It can It is used for detecting and estimating depth at which discontinuity occurs. So you will know the depth at which this crack is present. Okay, so that is what even the formula that we looked into, the distance is equal to V into T by 2. Okay, so you use this formula to find your distance. I mean, any of it, they'll give you two things and you have to find the other one. So the time delay between the launch of the pulse and the reception of the echo is monitored. So this first initial part is your launch, and then this is your echo. Your reflected part is your echo. The time delay between this is also monitored. Okay. So distance traveled by the acoustic beam, when launched normally into the test space before it is received by the detector at time t is 2D. So one way, two way. So it's 2D. Okay. So if this distance is d, then you are traveling both ways. Let's say 2D. And I told you before, d is equal to vt by 2 because it's 2D. That's why we have this. Okay. I mean, essentially d is equal to vt, but 2D is equal to vt by 2. Yeah, same thing mentioned here. So if this part is your d, then it's 2D. Yeah, it's distance mentioned. So distance equals to time into speed by 2. Now your pulse echo setup. This also is what will be asked for a 10 mark maybe for the first chapter because everything seems important for a 10 marker. But if I had to say, you might get pulse echo versus your equal loudness, uh, or they'll ask you for piezoelectric magnetostics. Maybe they'll just ask you the ways to detect your ultrasonic waves. What are the different things, methods that you use? So you use your, you can use piezoelectric magnetics and all of that you can talk about. So it could be one among these, but pulse echo is also a really, you can expect it. So yeah, first we will see what the diagram is. The diagram here is. So this is your A mode scan. Okay. So A mode scan, what does it essentially tell? It's the amplitude with respect to time. So the more it is, the more amplitude there is. So A, B, B dash and C. Then this is your receiver and your transmitter. So you transmit as you see the crack. So this B is a crack. You reflect, and then this is getting sensed by the reflector, and then you amplify it because I told you there's only accidents. So some of it will be going below, somewhere scattered, and depending on the crack. No? Your crack will not always be smooth, so it will be irregular. So some only a part of it will be reflected. So that you have to amplify also. So based on the amplifier, you will actually put it to your CRO. Okay, your wait, I forgot the full form for CRO. How could I? Cathode ray oscilloscope. Yeah, cathode ray oscilloscope. So your whatever is amplified, it is sent to your vertical plate. Okay, so this will move up and down. So uh, amplification, some amount of wave that is sensed, then it moves up. Okay, so it moves up and down, and that's why we see the amplitude. This time-based generator, it keeps moving in the horizontal fashion. These two plates, they keep moving in the horizontal fashion because with increase in time, what is your amplitude? That is what you are essentially finding, no? That's all. I think that is the idea of the whole diagram. If you okay, now that you know this, the basic idea, these points you can very easily understand. Okay, so if you are thorough with the diagram, you can actually write all of this on your own. Just you need to remember like a flow or something. You can actually write it on your own. Okay, so time-based generator generates high frequency time pulses. A time-based generator, your time of your whole setup now. So it's gonna decide how I mean your time clock pulses, okay, your timing pulses. Uh, the ultrasonic frequency of driving the transducer is extracted from this high frequency clock cycle by using appropriate dividing counters. Okay, so essentially what they're saying is that so the ultrasonic frequency of the drive of for driving the transducer. So this is your transducer. You need to drive the uh, transducer, right? So for that, their ultrasonic frequency is derived from based on this time-based generator, so that you actually uh, drive your transducer. Okay, and then first if we talk about the time-based generator frequency for driving the transducer. The ultrasonic pulse generator then switches this ultrasonic frequency on for a short duration. So it
A few tens of nanoseconds and switches it off for a wait period for which the transducer listens for echoes. So what does it say is that this ultrasonic pulse generator, see this time-based generator will have frequent highs and lows, no? Like at lows, nothing happens. At highs, there's something happening. So, I mean, the process should have go on. So this ultrasonic generator also keeps a track of it. So only when it's the high period, it will generate it. It will generate the ultrasonic pulse. So in this low period, it will wait for it to receive the echoes back. So you transmit something, the echoes that is received. So it will wait for that time. So the time-based generator will note down how long there's a delay between transmission and the emission back, the echoes that is emitted back. Okay. So the ultrasonic pulse generator then switches this ultrasonic frequency on for a short duration and then it switches it off for a short for the other time so that it listens for the echoes. Okay. Then the amplified launch pulse is used to drive the transmitted transducer. So this amplifier is used to drive the transducer. So first you talk about the time-based generator, which is the clock of your entire thing. Then your ultrasonic pulse, it keeps it on for some time, it keeps it off for some time. And then your time-based generator is used to like drive your entire thing. And then you talk about your amplifier also. That is your first 4 points. It's all from your diagrams. The reflections received by the receiver transducer is amplified. This is used to drive the vertical plates of the CRO. So the CRO vertically up by a distance proportional to the amplitude of the received echo. Nothing. I've already explained this. So as there is transmission, there is some emission, there is just some echo. So that echo is amplified. That is what they're saying. The received reflection is amplified first. Okay. Then it goes to your vertical plates of your, I mean, vertical as in here, it's not the, your horizontal is your vertical here. Don't get confused with this. So your top and bottom ones, it actually moves up and down, which is proportional to your amplitude of your echo. Like the echo that you're getting, there's some amplitude to it, no? So it moves up and down. This, after it gets amplified, these plates, they move up and down. Okay. So that is what they say. So the CRO vertically by a distance proportional to the amplitude of the received echo. That's all. Meanwhile, the horizontal plates move horizontally in proportional to the time because they are time-based generators, no? These horizontal plates, this left and right. So these are horizontal plates that moves left and right based on the time. I mean, it moves right because with increase in time. The horizontal plates are therefore controlled using the time-based generator that we already know. Thus, the amplitude mode signal depicting amplitude of the received pulse is traced as a function of time on the CRO screen. So the CRO will have its own screen. So this whole thing is traced over there. Okay. If no echo is received within the wait period, the electron beam does not receive any signal on the vertical plate and therefore swept horizontally with a flat line. So if you see in the diagram here, this part, no, there's no amplitude at all. So your vertical plates don't move up and down. So only your horizontal plate, they move because there is, I mean, you increase in time, no? So with increase in time, you need to show that there is time that has gone. So you have your horizontal line. So this flat line is there then. Okay, flat line on the oscilloscope. The amplifier of the transducer can be designed to increase the gain as time elapses. Then amplifier can be designed to increase the gain. The received signal amplitude will increase as the time from the launch increases. So they're just selling to ensure any losses. You can try to gain, like ensure you actually have a better amplifier. That's all. I think it's all done. So such amplifiers which have a time dependent gain is called as swept gain amplifier. So essentially this is based on your time, like when you receive it, there is some delay in your transmission and emission, no? So your amplification based on your time is your swept gain amplifier. uh, so yeah, I hope you understood this is actually, it looks scary but it's a very simple thing. So first, time base, that is your clock. Your ultrasonic pulse generator, it goes highs and lows. Depending on that, the ultrasonic will be generated. Your amplifier amplifies. It ensures it drives the transducer. Then you actually see your transmission and there's echo that's generated and that is amplified. That actually makes your vertical plates of your CRO move up and down. So hence you find your amplitude variation over here. And then similarly, a time-based generator makes your horizontal plates move left and, I mean, moves right with increase in time. And if there is any idle period, then only the time moves and the amplitude doesn't move. I hope I cover everything. And then you just write your swept gain amplifier is based on your time. So I think this is all that you need. It's a very easy thing. Just looks scary. That's all. Okay, and an amplitude. I told you it's based on A mode scan. It's based on your amplitude and time. Okay, and then your B mode scan. No, that is based on your amplitude. It's based on your transducer position and echoes at each. So here A is more highlighted. No, that means there's more intensity or more amplitude for A. Like okay, if you compare these two, A is the highest. So for you for that the more darker shade. Then B and B dash almost similar shade, and C is like slightly dark, slightly less darker than A, or like similar to A. I mean, it depends. Okay, so that's all. So this is what your B mode scan is. Okay, so I think we're done with this part. The representation of A, B mode, and C mode is something to look into right now. Yeah. So if you see here, uh, you're scanning from left to right. So how will you draw your A mode scan? So first, every time you will look into your A mode. If you see here, you will actually hit A, right? So as you hit A, you actually draw some amplitude of of some strength. Okay. Then again, you start moving, and then you notice B. Okay. So B also you draw your amplitude. Then comes your C. Essentially, how will you decide your amplitude? This is more distance. So there's a lot of it that will be wasted. So there'll be comparatively lesser amplitude. So B now, since you're scanning from here and again going back, comparatively more amplitude. This is not like exactly accurate, but if you see here, A should be slightly lesser than B. And C should be more because there's not much loss that you can expect. You just reach C, again you go back to the echo goes back. So I don't think the amplitude is wasted as much. Okay. So, and then this back wall, all of this area. So you will, if you actually scan throughout, you will also scan this part, no? So this is your back wall part. So back wall will be the lowest because there's more distance. Like you come here, come back, go there. There's more you lose. So your back wall. IP is your the incident thing, what the incident thing which is always higher. Okay. Scan, I think it's done. It's just theory that okay, whatever I explained, it's all put in words. You just need to like put it in like better English, better technical terms. Okay, now B mode scan. So this is something that you will be like frequently tested upon. So if you see, if you start from this, you start scanning from the left, you notice A. So this throughout this whole part, you mark one line. So that's what you see here. Okay. Then you scan. Actually, there's one other concept of it. So you actually scan through this area also, right? Before B and between A and B, this part. So actually, you put a back wall here. Okay. But this part, you actually don't put a back wall here when your pressure is uh, not high enough. Okay. If to not high enough to cross through the crack. When the pressure is not high enough to cross through the crack, then it won't come here. But if there is enough pressure, then you can actually draw a back wall even here also. Okay. So you can draw it throughout. Okay. When there's no high pressure enough to beat through this crack. When there's enough pressure. Okay. So yeah. Now B you just draw this when you encounter B, then C you draw this. IP is the initial thing. That's all same just examples, different examples. Okay. If you see here, power. Why was I talking pressure? Okay, power. Most of the times, the ultrasonic power launched into the test piece gets reflected back if any crack or discontinuity is present. Okay. So if you see here, there is um, Here they've drawn for A mode, this is fine. For B mode, they've drawn only at these intervals. Okay, so there is no enough pressure power to actually cross through the crack. Okay, in the question they'll definitely mention. Okay, they'll mention whether the ray actually passes through the crack or not, whether there's enough power there. So depending on that, you actually draw your back wall, whether you draw it or not. Again, all of this is just theory, just explanation of whatever I told right now. Okay, your C mode scan is essentially all of your medical kind of scans, all of that. So you just draw an example from top mode, bottom mode, and then that this one famous example that this coin example. So this is like the top surface, okay, and then this is your bottom surface. It more or less looks the same only. So you can just draw partitions everywhere. Every unit you can draw partitions and you can scan. That is how the scanning happens from left to right. You actually use your transducer and traverse through the whole thing. Okay. So that's how you sense what is there. Yeah, it's all the same thing. C mode medical sonogram. It is used in sonogram. You scan through everything and then you lay your plot. So if you scan through, if you connect it all up, you'll end up getting all of this final picture. So all of this, just draw any and every question, just try and draw as much as possible. I think it should do. So yeah, just if you connect it, you'll get your final thing. So it's used in sonography, all of that. Your C mode scan, which is time motion scan, which is your compound B mode scan. The same thing as I mentioned, just cut through everything and you capture the 3D image by plotting the points. So uh, see, it is actually seen over a period of time. So movement is expected or noticed, and then they keep recording the changes as a video file. So over a period of time, they actually change all of this. So I mean, they notice, they traverse through the whole thing. They use a transducer and traverse through the whole thing. So over a period of time, it changes. So that they record as a video file. So in medical field mainly. Uh, yeah. So okay, during expansion, during contraction, this and all is not much necessary. This also not needed. I think it's just extra information given here. Okay, these are all questions that's there. I think if we find time, we can deal with it later. But these are the question papers, I think, from previous years. So I think we are done with unit 1 finally.